Hi guys, this video today is a fun day because we get to learn a new operation, and that operation is logarithms. It is a little bit like, do you remember when you were maybe in kindergarten or first grade and you had learned how to add and you were feeling great about adding, and then all of a sudden your teacher says, hey, guess what? There's this other thing called subtracting, and it's the opposite of adding. And your mind was blown and you had no idea how you were going to cope with it, but you did. You got through it and now you know how to subtract. Okay, that's a little bit like logs. Let's talk about logs. Most every operation has an inverse. That's like the opposite of it, right? So addition, the opposite is subtraction. Multiplication, the opposite is division. What about x squared? What is the opposite of that? Well, it's a square root. Well, what about exponents? What is the opposite of exponents? And the opposite of exponents is logarithms. And so if you know how to do exponents, which you do, then now you just have to train your brain to go backwards. And if you go backwards from exponents, you get to logarithms. And that sounds a little bit confusing right now, but we're going to work through it. So I have a couple of things. Over here on the right, b to the x power is a. So let's just say that we're going to use those letters, b, x, and a. You can use any letters. Different textbooks use different letters. Do you know that in this, the b is the base and the x, of course, is the exponent? Well, then we change this and we say log base b of a is equal to x. Okay, but just how we say that in words, we say the log base b of a is x. That's how you say this sentence, where b is your base, x is your exponent, and a is like your answer. And so those letters are all here, but they're also here. They're just kind of mixed up in a different order. And if you look at what order they're going in, sometimes I say that we're going to go left, right, left. Or if we go the other way, we go right, left, right. You're going back and forth when you do this. So let's look at some examples. Let's say you have log base 5 of 25 is 2. I could rewrite that as an exponent. 5 is my base, so I always start with that base. 5 to the second is 25. And so again, look at how I'm going left, right, left. So I come over here, I go left, right, left. So 5 to the second is 25, left, right, left. All right, how about 3? Log base 3 of 81 is 4. Okay, then we start with our 3 and we say 3 to the fourth is 81. We're going to keep going. Left, right, left. 9 to the first is 9. Now, we're going to do some more of these, but we also, if you look at the other table, we also will be going the other way. And so, for instance, 3 to the fifth is 243. The way we would write that as a log is we would say log base 3 of 243 is 5. So once again, we go left, right, left. Okay, let's look at the next one. We're going to start off with log base. The base is 10 because it's like the base of the exponent. It's still that same base. Log base 10 of 1 is 0. We go left, right, left. Similar deal here because we have a log base 10. So log base 10 of 10,000 is 4. Okay, I started a couple of these on each table. Will you take a minute to see if you can finish out this table and also finish out this table? You're going left, right, left on each one, changing it to exponent, changing it to log. Okay, so take a minute to look at the tables of how I filled these out. Check your answers. But also, while you're checking those, or maybe take a minute to pause it to check those answers, let me talk about what I was talking about before. And that is how logs are the opposite or the inverse of exponents. Because what we're going to be doing is we're going to be asked, like, let's just pick this log base 3 of 81, okay? We're going to be asked, okay, what's the log base 3 of 81? And so in your mind, you have to think backwards and you have to think 3 to what power is 81? And that's what you're going to be training your brain to get your brain wrapped around to figure out how to get those. So again, check answers on these, make sure you have them right, and then let's do some examples. So in this section, I have set them equal to x. A lot of times in the book or on Delta maybe, they won't have equals x. They'll just say, what is log base 8 of 64? And so what you're asking yourself is 8 to what power is 64? That's what you're asking yourself when you see that question. Well, most of us now, if we read it that way, we know what that answer is. We have that in our head because we've learned our exponents. 8 to what power is 64? 2. 8 to the second is 64. And so that's basically what this question is asking is, what power would give us that answer? Okay, but I put in those x's so that we can make some sense of it. In other words, so that we can go back to doing what we were doing in this table. So this is like saying 3 to what power is 81? Now, you're going to have to know your powers a little bit or be willing to do some guess and check on your calculator. And so, for instance, on your calculator, you could type in what's 3 to the second. Well, you probably already know what 3 to the second is. Try 3 to the second, try 3 to the third, try 3 to the fourth, and try 3 to the fifth, etc., until you come up with it. So if I go to my calculator, I can just try, okay, what's 3 to the third? It's not big enough. Okay, what's 3 to the fourth? 81. 81 is what we were looking for. So the answer here is 4. So 3 to the fourth is 81. Let me pick another easy one before, because number 3 has a fraction in it. Kind of scary, right? Let's kind of skip that for a second. But number 4, you can do number 4. Everyone right now try number 4 on your own. Okay, if you had to think about it, that's okay. You write it out, say 10 to the x power is 100. Well, that would be 2. 10 to the second is 100. So that's how you do those. Okay, let's get into some of these scarier ones here. Number 3, log base 4 of 1 over 16. What's that answer? Okay, to find that answer, I'm going to come over here so I've got more space. We're going to say 4 to the x power is 1 over 16. Well, the fraction is what's throwing you off, right? You're kind of intimidated by that fraction. And so we have to think about, okay, how are we going to do that? Remember that a negative power gives us a denominator. So in other words, if we think about it, 4 to the negative first is 1 over 4. 4 to the negative second is 1 over 16. So x is negative 2 because 4 to the negative second is 1 over 16. Remember, 4 squared is 16. 4 squared is 16, so 4 to the negative 2 is 1 over 16. I'm looking at the other ones and trying to decide which one to do next because I want to make it, within reason for you. So let's try number 6. Let's say we just go to the converting it to exponent and we say 9 to the x power is 27. Well, we know it's not 1 because that would be 9. That doesn't work. We know it's not 2 because that would be 81, and that doesn't work. So it's somewhere between 1 and 2. The question is where? Where between 1 and 2 is it? We have to look at these and decide what is the common base. What number would go into both of these in an exponential way? And maybe before I even start this problem, I should say you will definitely be expected to do numbers 1 through 4 in your head. You can't do it yet because you just learned it, just like you couldn't do subtraction the first day you learned it. So we will be working on these and doing these in your head. But you should eventually, pretty quickly, be able to do numbers 1 through 4 in your head. Numbers 5, 6, and 7 are kind of the advanced version. This is Honors Algebra 2, and so we're going into a little bit of, this would be the honors stuff. Honestly, I don't know if your regular Algebra 2 people have to do this, but regular Algebra 2 people do have to do 1 through 4. Okay, so with that in mind, let's think about this. So what I was saying is each of these has like a common base to it. Have you thought about what that base would be? It's 3, because 3 squared is 9, and 3 to the third is 27. Now I left something off, didn't I? I have this x. So 3 squared to the x, that's 9 to the x. So it's the same thing. I can rewrite it that way. And 3 to the third is 27, so I can rewrite it this way. Okay, now we're going to make a little bit of a jump. And this is actually a rule a property, but for now, let's just kind of take it logically. If both of these have a base of 3, then shouldn't that exponent be equal to each other? In other words, shouldn't that 2x be equal to 3? Because they have the same base. And so 2x should be equal to 3 because 3 to this is equal to 3 to that, right? So this is going to work out. So now we're going to divide by 2, and we get x equals 3 over 2. Let's go and think about this a little bit more. One thing is, we said in the beginning it's between 1 and 2. We got that. Another thing is, let's think about this. If x is 3 halves, then let's go back to our original, how we rewrote it as a exponent. 9 to the 3 halves power. Do you remember last unit we talked a little bit about this? That 9 to the 3 halves power means the square root of 9 to the third. We did that last unit. And the square root of 9 is 3, and 3 to the third is 27. So it does work out. So that's like how you can kind of check your answer. But how do you even get there? Well, to get there, you have to find that common base and then do a little bit of logical conclusions to come up with 2x equals 3. Okay, let's do another example because I know that is not an easy problem. All right, number 5. Log base 64 of 1 over 32 is x. Let's convert it to an exponent. 64 to the x power is 1 over 32. 32 and 64 are really similar, right? 32 times 2 is 64. But we don't want times, we want powers. So what power would each of these, what base could we have that we could take it to a power? So the number that I'm thinking of is 2. Okay, 2 to the 6th power is 64. And 2 to the 5th power is 32. But we don't have 32, do we? We have negative 32, 1 over 32. And a 1 over 32 is a negative 5. So now, back to that logic, they're both the same base. And so we can just say 6x equals negative 5. And so therefore, x must be equal to negative 5 over 6 because I divide by 6 to get that x by itself. That logic, once again, there's a lot of steps there. So first of all, figuring out they have the common base of 2, 2 to the 6th, 2 to the negative 5th. Secondly, thinking about that logic that if they're both to a power and they have the same base, then those powers must be equal to each other. And that's how we get our answer. One last question. This is similar to a lot of them that we've done. Take a minute to look at this. Can you, first of all, set it up as an exponent? And secondly, can you work this out, do you think? 243 to the x power is 1 over 27. I left off the x this time. It's true. But remember, I started off by saying that x won't always be there usually. I'm doing it so we can figure out how to set these up, but it's not always there. So you had to figure that out. Then you had to think of what's that common base, and it is 3. And you might have had to go to your calculator. So a minute ago, we were doing these 3s. We said 3 to the 3rd, 3 to the 4th. What about 3 to the 5th? And 3 to the 5th is 243. So we come over here, we change this to 3 to the 5th to the x power. 27 is 3 to the negative 3, because 3 to the 3rd is 27, so 3 to the negative 3 is 1 over 27. Now we can drop that common base and just say 5x is equal to negative 3, and we get our answer. That's how you evaluate logs. The main thing is you think 8 to what power is 64? 10 to what power is 100? 243 to what power is 1 over 27? So this is kind of the question that you're asking yourself. And if you get stuck and you're not really sure how to set it up, think about left, right, or right, left, right. Depends on which way you're going. Like there will be some problems later on. Right now we're pretty much sticking with left, right, left, but we might come to some points in like an equation solving where you have to go the other way. You know, in equations you sometimes go backwards. So we might go right, left, right in equations. Two last concepts, and those are common log and natural log. Common log is log base 10. It's called the common log. If no base is written, the base is assumed to be 10. For example, log of 5 means log base 10 of 5. And this is a common log because, it's common. It occurs a lot in our world, and we'll look at some of those examples. A lot of times in these examples, it'll be a little bit like scientific notation in a way. So let's take a look at number 1. If this is log base 10, then we're asking ourselves, 10 to what power is 100? We had that problem earlier, and the answer was 2. So the log of 100, the answer is 2. Well, back to that scientific notation thing. What if it's a decimal? Well, if it's decimal, that means you go the other way. So this is actually negative 2. 10 to the negative 2 means you move your decimal over 2 places. You can check this on your calculator, and we're going to do that in just a second. In fact, let's just go ahead and do it now. I'm going to show you some of your buttons on your calculator. So find your calculator, and we're going to locate a couple of buttons. The log button is the main one we're going to look at today. So to find the log button, if you go over next to the 7, you see the log. You'll notice up above it is 10 to the x power. That tells you that the log and 10 to the x are inverses of each other. There's another button down here that's the ln button that we will go to later in a minute. Your calculator does not have on the main screen a log base button. I will tell you there is a way to do log base on your calculator, and if you want to Google it, you can Google it. I'm not telling it to you right now because I think it's important that you know how to do this a little bit in your head. Just like when you were in kindergarten, your teacher made you learn subtraction without a calculator. I'm going to try to help you learn logs without a calculator, and then we'll go in and get logs. We'll go in and use the calculator. Log of 0.01. So we type in log 0.01 equals, and it is negative 2, which is what we just said a second ago. You could test it by typing in 10 to the negative second power, and that also equals 0.01. So these two functions are inverses of each other. Log of 0.01 is negative 2, and that was what was on our paper. Okay, can you answer these two questions? I think you can. Take a second to do it. Think about it. It's a lot like scientific notation. Okay, 10 to the fourth is 10,000. 10 to the negative fourth is 0.0001. And again, we could go back to our calculator and check that if you want to do that. The natural log, remember the other day we learned about e? Well, the natural log is the inverse of e. And so we call this one the common log, base 10, because it is common. I feel like natural log is almost even more common. If you watched that Better Explained video, and you didn't have to watch that one, it was honestly a little bit dry, but if you did, it goes into e, and it goes into how these two are so natural. That is how commonly they appear. Because they are inverses of each other, they basically cancel each other out. We didn't get into that. We got into it a little bit up above. Log base 9 of 9 is 1. But basically, anytime you have a base and a log that are the same, they cancel each other out. So with the natural log, we could call this log base e, but we don't. We call it natural log. And usually when I write it, I use a cursive L because that way it looks like an L, it doesn't look like a 1. But the natural log and the e cancel each other out and they leave you with a 1. But we can also do that on our calculator. So let's go back to our calculator and find out what is the natural log of 5. So on your calculator, that ln button is right by the 4. So if you type in ln of 5 equals 1.609. That's all that question is asking. It's just I'm trying to help you figure out how to use your calculator. One last one just for fun is a log of 22. And so on our calculator, if we type in log, which is by the 7, 22 is equal to 1.34. And what each of these means is this one means e to the 1.609 is equal to 5. And this one means 10 to the 1.34 is equal to 22. Maybe one last example over here. This came out to be 1. If I had the natural log of e to the third, that would be 3. If I had natural log of e to the 12th, that would be 12. Okay, because the natural log and e are inverses, they essentially cancel each other out. Okay, that is all for our video today. We will continue to work on logs, but this is an interesting concept, right? Trying to get your mind to work backwards from exponents. So we'll need to practice that a lot.